Hi everybody, and welcome to today's SimScale webinar on the effects of radiation on the thermal comfort of indoor spaces. My name is John Wild. I'm VP of Customer Success here with SimScale. That actually means I'm running a few different teams. So I'm looking after the pre-sales team and the post-sales team. So they're looking after our prospects and then our customers after they've subscribed with us at SimScale, and also product management. So if you have any questions or complaints about the product or ideas of where you'd like us to go in the future, I'm also the person to talk to. Our agenda for today, I'm going to spend a little bit of time talking just generally about the benefits of utilizing simulation, then a bit of an introduction into SimScale, who we are exactly and what we do. Then we'll dive into the topic. So we'll talk about radiation, which is new to SimScale. Very new. So it's not actually released to the public today, but it should be in the next couple of days, and then everybody can start to utilize it. I'm going to basically run through a project based on the SimScale office, and then I'll show it live on the platform, and we'll talk about some results and the different kinds of things that you can see. At that point, when we get to roughly around the level 4, the fourth point, one of my colleagues is going to send an email out to everybody who's on the call right now, and that'll give you a link to the project. And then you can basically, within SimScale, work through some of the results with me. And then we'll come back to the presentation to talk about some of the results in a little bit more detail before a Q&A at the end. If you do have questions as we go, feel free to ask them. I have a chat window open on the other screen, and I'll try and reply as we go. Just a quick question before we start. I've just popped a poll up onto everybody's screen, and I'm really interested, I guess, in knowing what your skill level is with simulation. So thanks for taking a little bit of time. I'll just wait for some results to come in, and then we'll talk about the results, and then it helps me to kind of figure out what to talk about during the next 30 minutes or so. Okay, cool. Interesting split. Somebody did, or different people have voted for everything, so which is cool. Some people are definitely very expert, which is awesome, but actually most of the group are within beginner and intermediate. So thanks for taking the time. It gives me an idea, of what to talk about right now, and I think that's really useful. So thanks. Okay, so a little bit just about the benefits of simulation before we dig into the specifics of SimScale. So we're talking today really about AEC, so looking at the kind of smaller topics within AEC. So we could utilize simulation for looking at really huge kind of cityscapes if we wanted to, perhaps looking at wind loading or pedestrian comfort in those regions, or we could look at kind of smaller regions, which is what we're wanting to do today. And that's going to help us to basically look at whether people are comfortable inside rooms, help us to form cooling or heating strategies within rooms. So where do we want to place cooling ducts or heating panels or radiators, for example. And so that kind of does two things. It helps us to make sure our occupants are comfortable, as optimum as we can be, and we can basically tweak the model and figure out within simulation before we build anything, how comfortable those people will be. And we can also look to improve energy efficiency. So maybe instead of using, 3, 4, 5 kind of cooling vents, maybe we could do with 1 or 2, depending on where they're located. And utilizing simulation, we can figure out what the best thing is. So a little introduction into who we are. We are a browser-based simulation software. We have CFD and FEA both in the browser, and everything is run in the cloud. So you don't need, and I also don't have, a decent, amazingly powerful laptop. You can do everything on a pretty cheap and easy to run laptop, and everything is done remotely in the cloud. So what we're trying to do is free designers and engineers, architects, anybody who could utilize simulation. We're trying to free them from the kind of local restraints that you often need, so local licensing, local hardware, and just giving you the freedom to do it wherever you are located. We can do everything all in one place. So like I said, we have CFD and FEA and a couple of other different solvers too, everything all in the same interface within the browser. So at the very beginning, you choose the analysis type you want to run, and everything gets a little bit customized depending on what you want to do. It's fast and I think simple and easy to use. So the idea is that there isn't too much of a learning curve, and we can also help you learn as you progress. So on the left-hand side, it also says we have real-time support. So I'll remember to show you in a little bit later as well, when we look within SimScale, you can have a live chat with us. So if you ever run into problems, in the moment when you have a problem, hit the blue speech bubble and start asking us some questions, and we can help you right there and then when you need it. So that's the other thing that helps you kind of get up to speed pretty quickly with SimScale. You can collaborate, so you can easily send a URL of your project to someone else. If they have an account, they can immediately view and see it. So you can very quickly, without having to download files or share files or any kind of big data, you can very quickly collaborate amongst a team, locally or globally. Okay, so to dig a little bit into today's topic, as I hope everybody on this call is aware, there are three different ways that heat can move around solids and fluids. The first two we've been able to do for a long time within SimScale. So the first one is conduction, and that is just heat moving through solid materials. The second one is convection, so that is basically heat passing from those warm or cold solids, so it's changing the temperature of the air next to the solid, and then that air or fluid or gas or whatever is happen to be moving next to the solid will then change in density and start to move around the room. So it could actually be moved, and that'll essentially move heat around the room. So it'll help things cool up, warm up or cool down. And that could be through forced convection. So you might have air being pumped into the room, as we do in this scenario that we'll look at shortly. Or you might just have a natural convection type of scenario. So just simply having a heat source in the room will, as you can see, if the convection and the person's hand getting a little bit warm, the heat is going to rise and the air in the room will move, albeit pretty slowly. It'll start to move around the room. The one thing we haven't been able to do until now is account for the third type of transmission of energy, and that is through radiation. So if you have, say, a radiator, or perhaps an easier thing to imagine is putting your hands in front of a fire pretty far away so you're not getting any kind of convection, you can really feel the heat, and that is the heat being radiated from the fire, the same as the sun, to your body. And that is what we haven't been able to do, but we can now. And I'm going to basically show you the types of results that we can see, and also how to set the model up. So once you have access to this within SimScale, you can also do the same thing for yourselves. And my colleague also shared that she has now sent the email out. So in your inboxes, you should have a link to the project, and we can take a look at this together once we get into it. I'm going to do a little bit more talking about the type of problem that we have first, and then I'll get into the interface also. So one of the reasons why it's important to capture radiation, if we take a look at this room, we have a heater on the right hand side. If we don't account for radiation, what is going to happen is that the heater heats up the air only locally, and that is going to rise. And then it's obviously going to rise and move around the room and then cool down as it moves and then fall down again. So we're going to have kind of like a warm region at the top of the room and a low region at the bottom. And that kind of stratification can happen anyway, and it's pretty common, and even with radiation it can happen. But the other thing that happens if we do have radiation is that the heat could move from one side of the room to the other regardless of how the air is moving. So it helps to distribute the heat. And especially if you've got a person sitting in the room, with the first scenario, they might feel a little cold. With the second, with the heat simply radiated to them, they could or should feel a little bit warmer. So, and you really, when you're looking at if somebody is comfortable or not in a space, you need to account for that radiative effect. So I'm going to talk a little bit about the project that we're looking at today, and then run through the setup as well within SimScale. Feel free as you go to ask questions again within chat. I'll happily answer them as we go if I can. If not, then I might leave a few towards the end. Okay, so once you're in the SimScale interface, and I'll show you this as well in a second, there are three kind of main steps to go through. The first one is to import your CAD. So that's the one thing that we aren't doing right now. So within your CAD system, you basically need to create your 3D model and you upload it into SimScale. Once it's there, then you can essentially the fun starts, and you can start to create all the beautiful images and get some really nice results and interrogate your model. The second step is to set up your simulation. So this is where we tell SimScale what we know. So we might know that we've got flow rates, we know that we've got heat loads, we know what the ambient temperatures are inside, outside, we know that we've got windows, we know we've got radiators, those kind of things. That's what we tell SimScale. And then once the analysis is run between 2 and 3, we get to start to see the results based on what we've told SimScale, and then we can start to make some design decisions. So we can then start to say, okay, are these people comfortable? Are they too hot? Are they too cold? Is the flow moving too fast here, too slowly? Can we move radiators? Can we move vents? And we can start to optimize and make our design as efficient as possible. So this is a small part of the SimScale office. There's about 85 of us in this office, so this is really a small part. Actually, this is where part of where I sit, and also part of where marketing and sales sit, out of interest. And I'll in a little bit point out where my seat is, just out of interest. This is not super representative of the office because being in Bavaria, we actually don't have any air conditioning, so it gets pretty cold in the winter and pretty warm in the summer. But we've tried to play a little bit with it, so we've added some radiative panels on the ceilings. And what we want to do is basically make a comparison between the exact setup that we have here with radiation off and radiation on to see, how much difference does it really make. And really what we want to know and what our customers will basically test is if I run with radiation, do the results change? Do I even need to have radiation enabled in this study, and will it make a difference? In this case, we'll find out that yes, it really does make a difference. Okay, so we have a couple of the rooms split up into a couple of regions and actually a kitchen along the bottom there. And basically the air enters from a load of different vents on the ceiling and can exit on the left-hand side out of some walls. We have a few heating panels on the ceiling as well. We have on the right-hand side some super expertly modeled people, beautiful cylinders, which is very excellent, and we have some furniture dotted around the room as well. So basically chairs, computers, anything that is a potential heat source or could potentially change how the flow moves. We want to basically model those things. This is where I sit, not right now because I'm in a relatively soundproof room, but normally. Okay, and this is our setup. So we're going to be using the convective heat transfer type of simulation in SimScale, which is basically only capturing the fluid volume, running it steady state, although we could, if we wanted to, run transiently, so things would then change over time. This is essentially asking if we had this situation infinitely, what would the ultimate temperatures be? With the blue arrows, you'll see that we have some cold air entering at various points on the ceiling. It exits as warmer air on the right-hand side, and we have a few heating panels, and those are basically marked in yellow, so the heat, when radiation is on, will radiate downwards into the room. When it's off, it can only be convected into the room, so the heat will then have to move pretty differently from those panels. Okay, so hopefully that explains what we have, what we want to see, and I'm just going to jump into SimScale basically to talk a little bit about what we will see or what we can see in the results, how we can kind of interrogate things, and then we'll talk about the setup. So this is SimScale. Everything is in the browser, as I said before, and we can very quickly kind of take a look around the room and see what we want to see. So the solids here are shaded by radiative heat flux, and you can see the scale here on the left, so going from essentially negative to positive, and my cut plane cutting through the middle is shaded by velocity, and that is basically blue is nearly or will be 0, so there's no or very minimal air moving where it's darker, and where it's lighter, this is where the velocity is higher, so the air is moving faster and it's coming from these vents on the top. I know that you have access to this too, so if you want to take a look, you're more than welcome to. You'll initially be brought, I think, to a dashboard like this, where you can basically, this is our public dashboard actually, but you'll see the project and you'll be able to open it from here or with a button on the top right. And then basically once you're in, if you want to, what I've done is expand the radiative convection project, and then gone down to within my simulation run and auto mesh, and then just post-process results, and that basically will bring you to where we are. There's a few different things set up already that you can basically turn on or off if you want to, and we can also create our own as we go. So we've got a couple of different cutting planes in the model. You can always just add one, and that'll just put a cut plane straight through the model. So this is cutting through there, and we can say, okay, show me temperature on this cut plane. And it's clipping the model right now, so I could turn that off. So this basically means that we can start to say, okay, let's take a look at the model and understand, where people are comfortable, where they're not. What is the temperature in different regions? What is the flow rate? So instead of showing temperature, I could show velocity. So I'm going to choose all velocity, which is essentially the magnitude. And that will then give me an idea of how the flow is moving around the room, where people are going to feel comfortable, where they'll feel a little bit drafty. You can also then turn the cut planes off, so just by clicking on the eye, they're still there, but you can turn them on or off as you go. I've got an ISO volume, which is basically showing me a range of temperature, so between 290 and 292 Kelvin. Everything within these surfaces is of that temperature, and it's also shaded by velocity. So what this is useful for is to say, okay, if there's a region where I've got very, say, low temperature, what is the velocity in that region, and is the flow rate what is causing the low temperature? So being able to shade it by a different variable helps to get an understanding of what is happening here. Just turning that off and turning particle traces on. Basically, these are essentially seeded from a couple of different points in the model. So one of the inlets over here on the right has something like 20 by 20 traces, I think. Yeah, so like 400 traces basically coming in here, and you can get an idea of where the flow goes. So it falls downwards basically to the floor, and then it starts to spin and rotate through the model. And that helps us to understand, okay, if someone is standing here, will they be comfortable? Will they feel the velocity from this vent? Will it be uncomfortable? And we can then start to think, okay, maybe we could have a different type of diffuser, so the flow could come out differently rather than vertically, and we can start to optimize our design already. Okay, I want to very quickly just run through as well how we get to this point. So again, going back to the three things to do within SimScale, the first one up here on the right is upload your geometry. So you can simply drag and drop your CAD file here, or CAD files. You can upload it, or you can import directly from Onshape. Being cloud-based, it will import directly from their cloud to ours. I'm going to talk very quickly about the first model that we have, the convective heat transfer, before looking at the one with radiation. The setup is very slightly different, so there are a couple of different and additional options that we can take a look at. So once we've got our geometry here, basically we would go, okay, create simulation. And that'll bring up the analysis types, and we can choose from any of these. What I've chosen is the convective heat transfer type, as you'll see here. And this is where we can say turn radiation on or off. We could run steady state, so an infinite point in time, or we could run transiently if something is changing over time. This model we run initially with radiation off and a steady state analysis. We then need to tell SimScale what we know. So basically I'm going to skip a few of these things and really focus on the boundary conditions, because this is what has changed the most with the addition of radiation. So this is obviously without radiation right now. So we have a velocity inlet, and you can add a boundary condition just by hitting the plus button and picking one of the boundary conditions that we want to choose, and then choosing the surface that it's applied to. And you'll see down here we've got the inlets. We have a flow rate going downwards in the negative Z direction, and then the bottom right you can see that that is downwards in the model at a fixed temperature. We have our outlets on the walls, so some on the right and some on the left. We have our radiant heating panels, so these have a fixed heat flux over watts per meter squared. We have our humans sitting inside, so if I right click and hide a face, you'll see them just standing inside there. Again, they have a heat flux applied to them. And we have our windows. So there's 4 windows on the left hand side. Okay, and from that point then we would add a new simulation run, which would basically give us something down here. You'll see there's a couple of different meshes, one where we spent some time trying to get a really great mesh, and one that I ran yesterday with an automatic mesh. Once we click on the automatic mesh, we can then start to post-process our results. So this will take us to a similar view to what we had before, but this time not showing anything to do with radiation. So this is everything without radiation. Again, it's all in the browser. Everything, as I said before, is cloud-based, so this is looking at a server located remotely. So my local machine does not have to do anything. Okay, and then once it's loaded, again, I've set up a few different things that you'll be able to take a look at. We've got a cut plane here on the cut planes, and I've called it vertical, and we could say move it around a little bit to maybe the same point as before. So now it's underneath one of those vents. We can get an idea, you know, of how the flow moves around the model. It might be better to say clip it and cut the model in two, and then we can get a little bit of a better idea of what is happening inside. Maybe if we move it sideways, perhaps downwards, we can start to say, okay, around these people, what is the flow speed? You know, how comfortable are these people going to be? And if I click on the E up here, basically I can pick an element in the model and get an idea of what the flow speed is going to be and whether they're going to be comfortable. And we can do the same for temperature as well. So if I change from velocity to temperature on the cut plane, again I can start to pick results and it will tell me, okay, the temperature in this particular point, and I can start to figure out, okay, are these people going to be comfortable or not? What we spoke about before, though, obviously, is that this does not include radiation, and that is what we came here to do. So what I'm going to do is switch to the other analysis type. So most of these things were as before, and actually you could duplicate the initial setup if you wanted to, and you could just make a couple of tweaks and run this again, or you could change your CAD model and run it again to make some very quick comparisons between designs. So the main differences here with radiation are that radiation is enabled here, and then within the boundary conditions as well, they look a little bit different now. So for our velocity inlets, we have a behavior. So basically we're saying, okay, radiation, if it hits these inlets, they're transparent, so it can simply escape, which makes sense. We could, if we wanted to, it doesn't make too much sense to say they're gray body, and then they would start to emit radiation too. Where this does make sense is on our radiant panels. So these are set to be gray body, and that means that basically they will radiate heat out into the space. And they will radiate heat to anything that they can see. And we'll take a look at what that means in a second. But basically it doesn't just go in a single direction, but it will spread out based on the direction of this face and what it can see from it. We have an emissivity value of 0.9, which means this basically has to range between 0 and 1, and that means basically if radiation reaches it, all radiation is absorbed and nothing is emitted, or the opposite direction, everything is reflected and nothing is absorbed. So the heat flux here is basically set the same as before, and we could as well, if we wanted to, set an additional radiative heat source. For these it doesn't make too much sense, but for our windows it might do. So basically down here we could say, okay, I mean this is obviously a very low heat source, but on a very sunny day, if the heat was exactly on these windows, this value could be higher. And then we would also have the additional solar radiation as well that would basically diffuse into the room. Okay, so there's not too much else different with the actual setup. I wanted to just explain as well before we jump back into the results. Actually, I'll load up the results and then I can explain how I got these. So basically on the left-hand side, you can see there's some camera icons. So basically I've created some screenshots from my results. Basically, if I click on one of them, you'll see that it's shown here, right? So, and we can also So the reason for having these basically is so we can very quickly, like this, share results with other people. So if I said, okay, check out my project, here's the URL, I can basically set up a few of these different images, and other users can very quickly flick between them and get an idea of what I've done and what I want them to focus in on. Okay, so before we jump back into the other project, I thought what I would do is just explain a little bit about the radiation and what we are looking at here exactly. So this is basically showing radiative heat flux on all of the surfaces that we see. So basically, where it's red, these regions are seeing a higher heat flux from everything else in the model. So basically these panels above are essentially radiating down onto these surfaces and making them warmer than they would be in the other model. And I'll explain that really quickly. So I think jumping back to the presentation will be easier to show you some of the comparisons between the two. So if we take a look initially on the ceiling level, looking at the temperature distribution on the left-hand side, this is without radiation. The heat can only be convected from those hot sources. So obviously we have a pretty warm ceiling. On the right-hand side, however, the heat can leave in a different way and is radiated to different surfaces throughout the model. So obviously that then gives us a much more realistic representation of reality. Again, if we look at this in a 3D way, you'll see on the left-hand side without radiation, the people are quite warm because then none of the heat that they are emitting is able to be radiated away from them. On the right-hand side, you'll see the people are a little bit cooler because their heat is allowed to be lost in a different way. Conversely, what we can also see if we take a look at, say, the tables and some of the furniture, they're not emitting any heat. On the left-hand side, they're a lot cooler. On the right-hand side, the heat is being radiated to them from both the radiative panels on the ceiling, which are essentially the same as radiators. They're basically a heat source that radiates outwards. So they're radiating to the tables, and also some of the radiation from the people would also basically heat up the local regions. And again, if we take a look at, this is a coupling, looking at one of the walls, we can see obviously the temperature on the left-hand side at the top is warmer because, again, the heat, it can only convect. On the right-hand side, it can radiate, so we get a slightly different temperature balance. I mean, bear in mind the scale on the right here isn't huge, but the temperatures do change, between sort of 5 and 10 degrees. This is focusing just on the solids. So again, we can see on the left, the solids look cooler. On the right-hand side, they look a bit warmer, which makes sense, right? Because like if we are standing underneath the sun or in front of a fire, we will feel the warmth from that heat source. So the average temperatures, as you'll see on the bottom lines, basically changes by around 5 degrees. So not massive, but it makes a really big difference when you're looking at occupant comfort. If we take a look at a couple of couplings across the model, again you'll see stratification in both models, which is normal and makes sense, but on the right-hand side the heat is a little bit more evenly distributed, so it's not only fixed to the top surface, it's able to be distributed a little bit smoother and nicer around the room. And if we look in a little bit more detail, so you'll see on the top right there's a line going from the floor to the ceiling. That translates to the graph going from left to right here. And we're comparing the two different studies side by side. So the blue line is the convection study. So the left-hand side, the floor is a little bit cooler, which makes sense because there's no radiation being emitted from any source to it. And on the right-hand side, it's a little bit warmer because the heat is only convecting from those heat sources and it isn't being able to be radiated out into the local room. Obviously, if we distribute the heat differently with radiation as well, then we will slightly change how the air moves through the room. So on the left-hand side, you'll see our human, this beautiful cylinder here, and the air basically being warmed up and rising as the density changes. On the right-hand side, the radiation controls the flow a little bit more. So the air does rise, but the flow patterns are entirely different. So we would need to totally, again, look at couplings and reassess whether these people are actually comfortable in the room or uncomfortable in the room. And again, if we look at something like ISO volumes or ISO surfaces, what we can do here, this is an ISO volume basically, and you'll see on the top there we set a range to where we know people will feel comfortable. On the left-hand side, there's a range, or there's an area here on the right-hand side of the left picture, where people will feel a little bit too cold. So the temperature here is below the comfortable region. On the right-hand side, everything within the room is going to feel quite comfortable. And if we look at traces, we'll see that the flow again moves a little bit differently. And we could essentially, if we wanted to, we could have traces coming from all of the different outlets or one at a time, depending on what we chose, to get an idea of how the flow moves. And again, where we have like jets of air or not, or recirculation regions where you might have stagnant air that gradually warms up, to help us to figure out whether these people are going to be comfortable, which is the ultimate goal. Okay, so just to summarize, with SimScale we are now, with the convective heat transfer analysis type, able to run studies that include radiation. You can have different heating and cooling sources, so we've got like our heating panels or our windows, for example. And that really helps us to understand what the effect of radiation is. So are people going to be more or less comfortable if we now account for radiation? Okay, I think that basically covers everything that I wanted to talk about today. Please, if you have any questions, post them in the chat. I think there's been a few so far, but I think I've answered everything as we've been. Yeah, I think yes. Okay. Okay, so there's one question that I can see that I haven't answered about what type of radiation model we're using. It's a view factor, a gray body radiation model. We're not, I don't think we plan to offer anything different. I think for the purposes of, or how SimScale is going to be used by all of our customers, that should be sufficient. But, you know, if you have any other thoughts, then please feel free to share. I'm definitely listening. Okay, so I'm going to very quickly jump back into the interface to talk about how we set things up with Windows. And basically, so one thing that we haven't got within SimScale is essentially directed radiation. So we're not going to see the solar radiation coming directly through the windows. It will basically diffuse as it reaches them, which for now is a pretty big step for us, but I don't think, well, to get here has been a big step, but I think anything else is going to be small steps. So we're looking at that in the future, but right now, just to talk about Windows basically, as David was asking, we would basically set up a heat transfer coefficient. So this is heat being lost to the external environment. So a value of, say, 5 watts per meter square Kelvin, up to maybe 10, would assume something like natural convection outside, and this is our ambient external temperature. If we say make this something like 20 or 25, now the flow outside is going to be moving a little bit faster with the same temperature, but it means heat will be lost a little bit faster. So this is only heat being lost. And then down here, basically, we have two things to do with radiation. So one is to say these are transparent. So any radiation that hits these surfaces from the inside is immediately lost to the outside, so it doesn't get bounced back or absorbed in any way. And we have an additional radiative heat source. Actually, this should be a much higher value, I would think, if it's basically has sunlight acting on it. And now radiation would also enter the room through these windows. But basically, they would be treated like a heat source, and using the view factors, the heat would be radiated outwards. So not in a direction from the sun, but diffusely into the room. I hope that answers your question. Someone asked a very smart question, and I'm surprised nobody asked it yet already. Can we visualize PMV and PPD, which is predicted mean vote? And these are like the two essential thermal comfort parameters. I would say very soon you can. Right now, so when we release radiation, no. We didn't have them before because they don't make sense without radiation, honestly. but within the next days to weeks, then yes, I would think that should be available. So then we can actually start to make the best of the fact that we have radiation on the platform. A couple of other questions about room temperatures. So the room temperature we started with, and what's the outside ambient temperature? So two things, right? One is that we've got the walls here. And if you wanted to, these are basically treated with no heat loss. If you wanted to, like the windows here, you could say, okay, they have a heat flux on them, like an external wall heat flux. And now heat will be lost or gained based on our ambient temperature. So if the internal temperature is lower than this, heat will come in. If it's higher, heat will go out. This was a steady state analysis, so there was no initial temperature, and there doesn't need to be assigned because we're saying what happens after an infinite amount of time. If we wanted to, we could run it transiently, and we could use initial conditions, and then we could assign temperatures to the air volume, and we could say, okay, how long does the room take to heat up or cool down based on our heat loads or losses. Okay, from what I can see, I've answered all of the questions I can see so far. So what I'll do is at this point say thank you very much for listening. I now I'm going to head home. Thanks very much. Have a nice day, everybody. See you.